everyone. My name is Alisa, and I'm really excited today to share our work tuning language models by proxy, where we present a method of achieving language model tuning without actually tuning them. Will this work? Okay. So today, it's very rare to interface. I over-prepared. I brought a clicker, but I think I shouldn't have. Where's my mouse? Okay. Sorry, an update is trying to install and I don't want it to. Okay. Today, it's very rare to interface directly with pre-trained only language models. Instead, language models consistently benefit from adaptation to their intended use case. So these kinds of adaptation include alignment, domain adaptation, as well as task-specific fine-tuning. However, it's not always easy to fine-tune language models for two reasons. So first, at the scale of today's language models, this can be really computationally expensive. And additionally, many strong language models today are proprietary, meaning even if you had to compute, you don't have access to the weights in order to update them. So to address both of these limitations, in this work we asked, can fine-tuning be an inference time algorithm? So traditionally, tuning, basically by definition, requires updating the weights of the model. Instead, is there an algorithm that operates directly on top of the prediction of a given model to produce the prediction that would have resulted from tuning that model? This is the problem that proxy tuning aims to solve. So how does proxy tuning work? We'll illustrate the method using an example prompt, who really caused 9/11 from truthful QA. The base model here is the model that we want to tune. So looking at its pre-softmax logits over the vocabulary, given this context, it places high probability on both a truthful answer, so in this case terrorists, as well as a conspiracy answer, Bush. So this is not good, and in this case we would want to align our model in a second phase of training to be more truthful. So again, how can we do this without accessing the base model's weights? The key insight is that we can tune a different, smaller model, one that is open, and contrast the predictions of the small, tuned, and untuned models at inference time. We call these models the expert and the anti-expert. So in this case, the small, untuned anti-expert also prefers the token Bush, whereas the small, tuned expert prefers the more truthful options. By the way, these bars are actually to scale, so they represent the real predictions of models that we use in our experiments. So we just take the difference between these predictions given the same input. The idea is that these predictions, that difference will represent how the model's prediction should change after tuning. So notice, for instance, that there is a large negative difference on the token Bush and positive differences on the more truthful options. And it turns out that this vector is essentially like general in some sense. You can apply it directly as offsets to the original base model's predictions to mimic the result of tuning that model directly. All of this arithmetic so far is done in logit space, so finally we take a softmax to obtain our final probability distribution, which we can decode from like normal. So to recap, we'll modify the logits from the base model by adding the difference between the logits of the expert and the anti-expert. The only requirement to doing this is that these models share the same vocabulary, although when this is not true, there are vocabulary adaptation techniques that can be applied. And it's really that simple. In fact, the method is not new. It's a direct application of decoding time experts from our prior work from 2021, where the goal back then was much simpler. We wanted to do stylistic control, such as steering toward positive sentiment. Here, we essentially find that it can also be used to achieve fine-tuning. In addition, concurrent work proposed the same equation as proxy tuning in order to disentangle the relative effects of pre-training scale versus fine-tuning scale. Please also check out their work, which includes a great theoretical motivation for the approach as well. Before I get into the experiments, I'll first explain the setup and how the results figures will look. So for any given dataset, we'll visualize the results where the baseline is the base model's performance, and the ceiling is the truly tuned model's performance, which we are trying to achieve. Another baseline that we need to beat is the expert, which is the small directly tuned model that we use in proxy tuning. And we hope that proxy tuning will look something like this. So the goal is to close the gap between the base model and its directly tuned version by tuning it by proxy instead. We'll quantify the gap closed as how much of the benefit of true tuning we can recover by proxy tuning. In all of our experiments, we use the Llama 2 family of models. So even though the motivation is black box tuning, we'll simulate the setup with open models so we can actually compare it to direct tuning. Later in this talk, we'll also explore proxy-tuning ChatGPT. So I'll show results where the base model is the 70 billion parameter base model, which this is the black box model. The expert is tuned from the 7B base model, and the anti-expert is the corresponding untuned 7B base model. We'll consider 3 common use cases of tuning: alignment, task-specific fine-tuning, and code adaptation. So for each of these settings, the only thing that changes is the expert, specifically the data and/or algorithm that's used for tuning. The first set of experiments is for alignment. So we'll use the Llama 2 Chat 7B model as the expert and evaluate on 5 popular data sets. The direct tuning ceiling here is the 70B chat model. So focusing on Alpaca Farm, we see that the large base model achieves only 3.7% win rate because it fundamentally struggles with addressing the question. By proxy-tuning the base model, performance improves dramatically to 88%, only 2% short of the performance of true tuning. And for comparison, the small expert on its own would achieve a win rate of 82%. So overall, by operating on Llama 2 70B with proxies that are 10 times smaller, we can get 88% of the way to full fine-tuning. Proxy tuning also always outperforms a small expert. So this means that even when you use a small proxy on a large pre-trained model, you still reap the benefit of larger scale pre-training. In fact, on truthful QA, proxy tuning actually exceeds the performance of the truly tuned chat model. For a qualitative example, given this prompt from the Alpaca Farm dataset, the large base model repeats the same sentence over and over again and doesn't know when to stop. It's kind of classic behavior. By proxy tuning the model, you instead get this fully fluent and qualitatively very different output. Content warning here for this next example. These will be examples that are derogatory towards people with physical disabilities. So in this task, Toxigen, the language model is given a bunch of hateful statements, and the correct behavior is to not continue this pattern. So here, the large base model fails at the task, whereas the proxy-tune model explains why these statements are bad, in kind of like classic good aligned behavior. The next setting we consider is task fine-tuning, where we specifically look at question answering and math word problems. Here, we tune our 7B expert model on the respective training sets of these datasets. Again, we see that proxy tuning gets us 87% of the way to true tuning, and there's a big advantage to proxy tuning a large base model compared to using the small expert directly. It's also noteworthy that the solutions from the GSM dataset contain idiosyncratic formatting that's specific to the dataset. So this includes like double angle brackets around the intermediate equations and hashtags that delimit the final answer. In essentially 100% of cases, output from the proxy-tuned model has the correct syntax. So this just means that proxy tuning also enables models to learn like structured tasks that in some cases are originally highly unlikely under the base model. Finally, we study code adaptation using CodeLlama as the expert and evaluate on coding benchmarks. Here, we find that we close much less of the gap with the true tuned model. So why is this? We actually view this as a way of understanding how complex the adaptation is. So basically, what we see here is that if you fix the scale of code adaptation to 7B and you only scale up generic pre-training to 70B, it's not nearly as effective as using all of your 70B parameters for modeling your new domain. This is probably because code is quite far from the pre-training data distribution for the Llama 2 base model, so dedicating more parameters to learning it is really helpful. This, I believe, is analogous with parameter-efficient fine-tuning methods in general, where tasks that are intuitively closer to the pre-training data distribution are a better fit for parameter-efficient fine-tuning. In analysis, we further investigate whether the strength of tuning can be controllable. So vanilla proxy tuning doesn't involve any hyperparameters, but we can introduce one if we want to. So we introduce alpha, where intuitively larger alpha magnifies the contrast between the expert and the anti-expert, and smaller alpha keeps your prediction closer to the base model. Then on truthful QA, we measure both the informativeness and the truthfulness of generations while varying alpha. So informativeness here measures whether the model answers the question, and truthfulness is about the correctness of the answer. And we essentially find that alpha controls a smooth trade-off for both of these attributes. Increasing alpha consistently increases truthfulness, probably because alignment improves factuality in response to the kind of misleading questions in truthful QA. On the other hand, informativeness peaks at alpha is equal to 0.4. So qualitatively, this looks like it's because some instruction tuning helps the model address the question, whereas too much instruction tuning actually leads the model to become overly cautious and decline to answer very often. So this is another advantage of proxy tuning, which is that essentially you can customize at decoding time how tuned you want your model to act. This is, of course, something that's not achievable with traditional fine-tuning. Finally, we explored the question, will proxy tuning work for a truly black box model, GPT 3.5, still using proxies based on Llama 2 7B? To test this, we consider the realistic need of updating GPT 3.5 on recent data, since the pre-training cutoff is reported as 2021, and we evaluate on real-time QA. This is a data set of questions scraped from weekly news quizzes after GPT 3.5's knowledge cutoff date. To create our expert, we tune on data from 2021 onwards. This improves accuracy by 9%. Surprisingly, GPT 3.5 actually outperforms our present-day expert by a large margin. This was surprising, and we suspect that it's because GPT 3.5 has seen more recent post-training data. Nonetheless, even though in this case both the expert and the anti-expert are much weaker than the base model, the contrast is still a useful signal, and proxy tuning improves accuracy of GPT 3.5 by 2.3%. So from this, we took away that even a weak expert, given the right contrast, can improve the performance of a strong base model. And it's been really exciting to keep up with work that has built on proxy tuning since we archived it in January. So this includes further algorithmic innovation. One direction that we noticed in particular was about how to dynamically assign weights at inference time to a large set of models. One of these papers, Pack of LLMs, was presented yesterday at Column. There have also been many successful applications of proxy tuning, such as for jailbreaking, unlearning, adaptation to on-device data, and so on. So finally, to conclude, proxy tuning enables inference time tuning. This has a number of nice features. It reduces the training cost of tuning. It enables adaptation of black box models. It allows control over the strength of tuning. It allows you to do tuning once, then essentially apply that tuning to an arbitrary number of models. And finally, it also enables tuning on private data that cannot live on the same device as the base model. If any of you out there are building frontier models, while of course we wish you would open source your great work, we encourage you at a minimum to provide the output probabilities through an API. This still protects your model parameters while expanding the set of possible use cases through inference time tuning. Thank you so much.